Hello and welcome to my channel. We have made a power supply for this robot arm, batteries. We also made a gripper for this robot arm, but it's not yet installed. In the next step, we should take care of the software, and for this we are going to use the Isaac Sim from NVIDIA. I also need to install this gripper. And I would like also to install these small heat sinks for the drivers for the axis 2, 3, 4 and 5. The axis 1 already has this heatsink. And for axis 6 and 7, I think the drivers should not heat too much, so probably I don't need them. But anyway, I have only 4. So axis 2, 3, 4 and 5. And if afterwards I will decide to also install one for the axis 6 and 7, it's way easier than for these two axes, especially 2 and 3. This should be nightmare. By the way, this video is going to be the foundation for the next video, and the next video is going to be about Isaac Lab. And I think this next video, first of all, is going to be extremely interesting and extremely challenging. So don't forget to subscribe to my channel in order not to miss it. These two videos are supported by NVIDIA, but I wanted to make this video myself, so I contacted NVIDIA about these videos and they agreed in order to support me. And I decided to make these videos because I think the Isaac Sim and Isaac Lab is really the best software for the robotics which you can find right now. And it's free. And Isaac Lab even open source, so really great combination. If you would like to learn more about robotics, watch this video till the end. Let's get started! First of all, what is Isaac Sim? Isaac Sim is a software which simplifies robotic simulation. But this software can do so many things that I think it's almost impossible to make a modern robot without Isaac Sim. Let me show you. The best place to start with NVIDIA Isaac Sim is developer.nvidia.com/isaac/sim webpage. And over here you can find what is Isaac Sim. NVIDIA Isaac Sim enables developers to simulate and test AI-driven robotic solutions in physically based virtual environments. So basically you can make the simulation of your robot inside Isaac Sim, and this simulation is going to be physically accurate. And you can simulate also all the sensors, including camera. And this is because Isaac Sim can make photorealistic images and videos for your camera, and like this you can train your camera inside the simulation. Over here you can find how the Isaac Sim works, and basically it can do not just the simulation, it can also do the synthetic data generation for your training, for the AI models training. And also you can use the Isaac Lab for the reinforcement learning. And this we are going to do in the next video. So Isaac Lab is for the next video. Here are very useful links, especially this one, Isaac Sim documentation. There are tons of interesting tutorials there. I also like the Isaac Sim courses. I think it's a great place to start. And Isaac Sim office hours live streams, also quite interesting. You can put your own robot in the Isaac Sim, or you can use one of the robots from the database, which includes also humanoids, manipulators and quadrupeds. How to get started with Isaac Sim, and some advanced stuff which you can do with it. In this video we are going to use a lot Isaac Sim documentation, this one. I really like this image because it shows that in the Isaac Sim you can design, tune, train and deploy different algorithms for your robot. I already made the video about Isaac Sim some time ago, but with the upgraded version of the Isaac Sim everything a little bit changed, so I would like to show these changes. And in this video I'm going to look way deeper into the Isaac Sim compared to the previous video. So first of all, it's going to be up-to-date video, and second, it's going to be more detailed video with more features. But not all the features, because there are so many features in the Isaac Sim. We're going to cover only basic ones. The Isaac Sim, you can use it either on your local PC, on desktop PC, or you can use it through the cloud. I'm going to use it on my local PC, so I'm going to install it on my local PC because it's easier. So the installation, and let's look at the requirements. This is actually quite big and complicated software which requires quite powerful PC. So for the minimum specs, Core i7 or Ryzen 5, 32 GB of RAM, and RTX 3070 for the GPU. My PC was built in order to have the good specification. So I have Ubuntu 22. I have AMD Ryzen 7 with 64 GB of RAM, and I have the RTX 4080, which was sponsored by NVIDIA. And very important, you should have a proper GPU driver installed. So here's the recommended version of this driver. I have decided to start with the fresh Ubuntu installation like this. Everything is clean and new. It is important to choose this one like this. We don't need to install the NVIDIA drivers separately. It's going to be installed automatically. So this is just saves time. The rest is a standard installation. This is a PC which I'm using. It has a lot of colors and it has RTX 4080, sponsored by NVIDIA. And by the way, this card is supported by the white 3D printed piece which is bolted to the fan. To install Isaac Sim, first we need to install Omniverse Launcher, which I downloaded from NVIDIA website. It's over here. To run it, we go to the terminal. Here I will copy this file to the documents folder and do sudo chmod in order to be able to execute this file. Now if I run this file, I got a message that I need to install libfuse2. So I did sudo apt install libfuse2 and it was installed. And now we can run Omniverse Launcher. Here we need to log in with NVIDIA account. This account is free. And after login, we accept license agreement, data collection and default settings. Next, we go to the Exchange tab. Here we are looking for the cache, this one. Install it with a single click. Next, we need to install Isaac Sim. Click install and wait when 9 GB of data will be downloaded and installed. For me, it took 10 minutes. Installation is complete, and now we can go to the Library tab. And finally, we can launch Isaac Sim. When I launched it first, I got this warning message which says that I should disable IOMMU in BIOS. And I have no idea what is IOMMU, but I disable it. Now I don't have this warning anymore, but we have this window where we can just press start. Basically here there is different possibilities how you can start your Isaac Sim. Most of the cases you're going to use the default one, so just press start. This is the main window of the Isaac Sim, and I think at this point the best thing is to start with the tutorials, which you can find on the Isaac Sim documentation website. So over here there is tutorials, and the first tutorial I think is super important if you never used Isaac Sim. So this is Isaac Sim interface and Isaac Sim workflows. The first one explains you the graphic user interface. So the first tutorial is super basic. It shows you that there is a main window, there is a window with all the objects which are present on the main window. And here there are some properties. And over here there is a useful table with the hotkey combinations to use the Isaac Sim. Next tutorial is Isaac Sim workflows. I don't explain these tutorials in details because they are basic ones and it's easy to follow them. There are 3 possible workflows for the Isaac Sim. The first one is GUI, graphic user interface. This one is good to set up your objects in the scene. This one is quite easy and simple. The second workflow is extensions. You can either use built-in extensions. There are a lot of useful extensions. We are going to use some of them. And you can write your own extension, Python-based extension. So like this, you are using graphic user interface plus these extensions. And the third workflow is standalone Python. In this workflow, you have control of everything. So this is maybe the most complicated way of working with the Isaac Sim, but at the same time, it gives you the most possibilities. Recommended usage, large-scale training for reinforcement learning. Haha, this is what we are looking for. This is not our goal for today, it's a goal for the future. The standalone application can be run with the graphic user interface or it can be run headless. In order to run the standalone application, you just need to run your Python code from the Isaac Sim folder, like here. You can also check my old video for the basic tutorials in the Isaac Sim. As the next step, I will install the gripper. So I dismounted the robot arm. Now I need to disassemble it, install the gripper. And why I would like to disassemble it? In order to install the heat sinks on the drivers 2, 3, 4, 5. And I think it's going to take me at least 1 full day or maybe even a couple days. Robot arm is disassembled. almost completely. And now I need to install these heat sinks. One here, one here, one here, one there. Put the additional cable for the gripper and reassemble everything. I have installed the heat sinks over here. I also installed the axis 2 and 3, and I already started to reassemble these two axes. I need to finish it. I need to do the axis 4, 5, 6, 7, and of course install the gripper. I have reassembled the robot arm with the heat sinks and with the gripper. Now let's test the gripper. I'm still using OpenRB 150. This is the software. Close, open, middle position, another position, another position, open, closed. And there is a LED. I can switch it on and off. It took me 2 days, but I have managed to make this URDF file. Look at this beautiful robot arm with the gripper, and all the joints works properly. This is the gripper, open, closed. The 7th degrees of freedom, 6th degrees of freedom, 5th degrees of freedom, 4th, 3rd, 2nd, and the first one. It's not complete URDF file because all inertia matrices, masses and center of masses are not correct values. To get them all correct, it takes a lot of time, like really a lot of time. I would spend at least a week for this URDF file to make it correct. But this is something with which we can start. And by the way, this is a really useful website where you can check your URDF file. You can put it on this website. You can look at how the joints rotates, and it's simple web-based. So this is a really helpful website. Now that we have a proper URDF file, we can add a new manipulator to the Isaac Sim. And fortunately, there is a dedicated tutorial for this. It even shows what you need to know before doing this tutorial. And after this is done, you can try to do this tutorial and the next one, which is the most interesting, this one. When this tutorial will be done, you would be able to do the path generation with RMP flow in the Isaac Sim. But our goal is to add our robot arm. So we are going to follow this adding a new manipulator tutorial. And afterwards we will synchronize this simulated robot with the physical one. So basically Isaac Sim is going to control our physical robot. And for this we need to create the robot USD file. So create the universal scene description file, which can be read by the Isaac Sim. And this file describes the robot, its joints, and everything which surrounds the physical stuff which surrounds this robot. In our case, it's going to be only a robot with all the joints and links. Afterwards, we will learn to control the gripper, and we will add the follow target task, and we are going to use the RMP flow to control our robot. So first of all, we need to create the robot USD file. For this, we need to import URDF file which we created before. Afterwards, we're going to do the inspect of the articulation. So basically, we're going to check that all the joints works properly. And afterwards, we're going to perform the gains tuning. And when this is done, we are going to save everything in the robot USD file, which we are going to use afterwards. In order to import URDF file, first we need to enable URDF importer extension. Here it is. In my case, it's already enabled. And we can run this extension over here, URDF importer. In the input, we choose our file. We check that the base link is fixed. And we need to uncheck brace mimic joint tag. Import. And here our robot arm. Over here you can see that there is a world, we have our robot arm, and we have the physics scene, and the default light in the environment. And over here we have all the links, and there is a joints at each link. This prismatic joint for the gripper. This is a revolute joint. Now, in order to inspect the articulation, we go to the window, simulation, this one, settings, physics inspector. We need to choose our arm and update. And over here we have all our joints. So for example, this one is the gripper. Open another finger, close, axis 7, axis 6, 5, 4, 3, 2, 1. Another useful extension is gain tuner. Sinusoidal gain test. It have rotated all the joints, and over here it shows how the commanded joint position follows the observed joint position. We have a little problem over here, but this is velocity, and the position was quite close. So everything looks quite well. If it's not going to be perfect, most of the time this is because you put the wrong either the torques or the weights of the links, and you can change it over here. And you can check the mass of the link, and you can also check the joint properties. Actually, if your robot arm is well built and your joint is powerful enough for the weights of this robot arm, and the speed with which you are moving is not too fast for this power which you have. And in this case, you will have a good convergence of the commanded position with the observed position. So when you put properly all the values for the mass, torque, etc., you can save this file, and like this you will have the USD robot file and use it afterwards. The next step is to control the gripper. This is not really necessary step, this is kind of intermediate step to understand how everything works. And in this step we need to create the Python code, which is written here for the Cobota robot arm, and I rewrote this code for my robot arm. We're using the simulation in the false headless mode, so meaning that with the head we need a world, and after we need our USD file, which we obtained previously. And this USD file, so this is basically our robot arm, we're going to add to our stage, to our world. Afterwards we define the gripper. So basically we need to define the link to which fingers of the grippers are attached. And afterwards we need to define the fingers, the one finger and the second finger. Afterwards we define the open position of the gripper, we define the closed position of the gripper. We define our manipulator, which we are taking from our scene. Here we define the default positions for our joints, and we put our arm in these default positions. We add the ground plane to our world, and we do the reset before each simulation. And the simulation loop is over here. So we do the stepping, we check the current position of the gripper, and afterwards we change the position of this gripper. So we basically open the gripper half of the time, and afterwards we close the gripper. So basically this simulation is going to show our robot arm in the default position, and the gripper is going to open and close, open and close. And now over here I'm running the code which I wrote, so the modified code. For this, first of all, I go to the Isaac Sim directory, this one, and over here I can run this gripper control Python code. And as I told you what this Python code do, it moves the fingers from the open to closed position. It's a very basic example, but I think it's very useful to understand how to work with the Isaac Sim in the standalone mode. Controlling the gripper works perfectly, and now we can do the next step, which is follow target task. This is quite challenging step. So first of all, we need to define the task, and we defined it in the folder tasks, and the name is follow target. So this is a Python code where we define the class follow target. And in this class we have the target, and over here we set our robot. And for this we use our robot USD file, and the rest is actually very similar of what we saw in the gripper file. So this is the task. After this, we don't need this one because we are going to skip the part of the step. We need the descriptor of the robot, YAML file, and this file is needed for the RMP flow controller. So this file is simple, so basically you need to put the names of your joints. We don't need this part, we don't need this one, and we go directly to the RMP flow to control the robot. We need the second YAML file, which is RMP flow common. And over here, there are tons of different parameters. And basically, I left all of them as default. The only two things which I changed is joint limit buffers. So we need to add another joint over here. So to have the 7 values instead of 6, because our robot arm has the 7 degrees of freedom. And I changed this link. So this link which is going to be controlled by the controller. So the link where the fingers of the robot arm of the gripper are connected. Ideally, I think I also need to change this one, but I have not touched it yet. And this is the controller itself. So this controller is going to calculate the exact joint positions. And the controller is defined over here. And as you can see, it needs a robot descriptor YAML file, the second RMP flow common YAML file. It needs the URDF file, the link to the URDF file, and it needs to know which link it should use as end effector. And afterwards, this file is doing everything. So basically, it assembles everything together. So there is a task over here. There is a controller over here. We create the world. We create the task. We add our task to the world, do the reset. We define our robot arm. Initialize the controller over here with our robot arm. And afterwards, we do the simulation with the stepping. And inside this simulation, we have quite interesting part, which is observations. Over here, we have the positions of all the joints of our robot arm. And by the way, what it's done here is that it takes the position and orientation of the target. It put this position inside the articulation controller. And this articulation controller is going to move our robot to the position where there is a target. And the target is a small cube. You will see it when we will launch this program. And again, to run it, we just need to run this Python code, follow target example, from the Isaac Sim folder. Let's see how it looks. This is the robot arm, and here I moved the target cube, and the robot follows this target cube. It tries to do the best job in order to follow this cube, and when the cube is not reachable, it just tries to be as close as possible to this cube. Also, you can rotate this cube, and it's quite interesting to play with the robot arm in this simulation. I think it's even a good idea to do such kind of simulation before building the robot arm, and not the other way around, as I usually do. Now what is left for us is to connect this simulated robot with the real robot. Here I have two programs. This is a modified Python program for my robot arm. So this one only does the simulation. There is no connection with the real physical robot over here. And this one, follow target example UDP. This one has the connection with the real physical robot. And the connection is done through the UDP. This means that this desktop computer, it connects to the Jetson Orin Nano, which is controlling the robot arm. And this desktop PC is UDP client, and on Jetson, I have installed UDP server. So on Jetson, there is another Python program which acts as UDP server. Here, there is a UDP connection. This is the IP of my Jetson, and this is a port which I'm using. This one is to add the checksum to the message which is going to be sent to the server, to the Jetson. So this function reads the reply from the Jetson, and from this reply it gets position and temperature of all joints, including gripper. This part over here is similar to the original file. Here I have the initial joint position, and now there is a simulation loop. This part in simulation loop is the same as in previous one, and the new part is over here, which is called send UDP. So basically what I do, I read the joint positions from the observations, and every 20 milliseconds I send the message to the Jetson in order to move the robot. And in this message there is a joint positions. So message sent is over here. Afterwards, I take the reply from the Jetson and I take the position and temperature. And every 50 iterations, I print the temperature of all the joints in the terminal on the desktop PC. So like this, I can control the temperature through the desktop PC. And if I see that this temperature is too high, what I can do, I can just stop the robot arm and wait when it cools down. But spoiler alert, the temperature was quite okay. It was not high at all. I was expecting way worse. So the changes in this program is not really huge. Just every 20 milliseconds, I send the message with the joint positions, I receive the reply, and I print the joint temperatures. I'm not going to discuss the Python program on the Jetson with the UDP server, because there is no Isaac Sim related stuff there. But in the description to this video, I will put the link to the Jetson UDP server file. Like this, if you are interested, you can look at it. And by the way, this UDP connection is done via Wi-Fi. So there is no wired connection between the desktop PC with the Isaac Sim and this Jetson which controls robot arm. Now let's see how it works. So the robot arm is connected over here to the battery. So it's powered by this battery. The signal goes to the USB to CAN bus adapter. And the signal from the gripper goes to this OpenRB 150. All these cables goes to the Jetson Orinana. Jetson Orinana is programmed by Konstantin. He's the best programmer ever known to humanity. So this is a magic on the Jetson. And Jetson is connected to the desktop PC via UDP. So there is a UDP server on the Jetson and UDP client on the desktop. And over here, we have the Isaac Sim with the robot arm, where we can move it. So now we can try to move it. And by the way, thanks to the belts and 3D printed gears, this robot arm is quite silent, which is a nice bonus. Temperature of the first one is 46, so the temperature is still okay-ish. It's not super high. It's still acceptable. Nice. I was afraid that the temperature is going to be the major problem, but apparently it's not so bad. Perfect, it works! New robot pilot. In the future, we can add the proper collision avoidance, the self-collision and also collision with the structure. And also we can add the perception with the camera. Isaac Sim allows for the photorealistic simulation, photorealistic scene simulation. And like this, you can use this data to train the algorithms for your camera. Good job! Don't forget to put the like to this video, subscribe to my channel, and also I would like to say a huge thank you to all people who support me via YouTube channel membership and Patreon. Here are their names. Thank you, you're the best. As usual, stay safe, good luck with your projects, and see you next time. Yeah!